So what I have on the top is a PMOS. Okay, so the PMOS has a biasing voltage, which is just a specific voltage, turn it on and keep it at a very good state. Okay, so it is on. It's passing VDD, not probably 100% of the VDD, but at least 80 to 90% of the VDD. So the pretty high voltage will be passed to here. And to open up these two PMOSes as a source voltage, not the gate voltage. Okay, so the gate voltage, the gates of the two PMOSes here are shorted to the signal to compare, and I set up the PMOS on this side to be the reference voltage, 0.5 volts. And keep in mind, this is using the 90 nanometer technology from, I don't know where this is from, like IBM. Anyway, so it's a 90 nanometer technology, and the VDD is just 1 volt. It's a low voltage application, or per size, which is low power per size as well. And the other side is a sine wave swinging around this offset voltage. So what's happening for these two? Because these two NMOSes here and here, these two are clocked. So the gates, you see a clock is shorted to it. So it's being clocked, which means these two pins, or these two nodes, will be shorted to ground periodically. Is that right? It just has a channel, two channels on the two sides, and it opens it up using the clock periodically, which means it pulls these two pins down to ground using the clock. Whenever it's high, whenever clock is high, it's going to pull these two points to ground to reset it. It's very popular. we'll have to figure out like why it works so well. Okay, it depends on like how we simulate it and a lot of analysis. So it's resetting these two pins, okay, to ground. So which means if you don't have anything, if you don't open up these two PMOSes, what's going to happen to these two nodes? If you just keep them, shut it down, okay, nothing. Yeah, it's going to be static ground. So like I ground it, use a solid ground, and then I cut it to make it float ground. Make sense? I discharge it, then I float it, but still ground. Okay, so it's actually making that 2 points to be ground. So if this voltage is higher than this voltage, what's going to happen? At some moment, okay? So because these two points are being shorted to ground or floating ground, but they are ground, are zeros, okay? If they are zeros, what does that mean? I mean, you got a 0 here, what's happening for the NMOSes? There's no current. Okay, you got a 0 volts here. It's being shorted to the gate for this NMOS. So this NMOS is off, right? The same to this NMOS as well. Same as this NMOS. So both of them are off. So before any current flows through the two PMOSes, it just opens up the pipe, but nothing flows through it. So the voltage will be transferred to the voltage nodes here first, before the current flows to it. It open it up, and then current start flowing.
So, but if 0 gets passed over to that NMOS, then that means that's turned off, and then that means whatever's up top gets pulled down, and then that goes over to the other NMOS gate, and then that turns on that NMOS gate, making ground getting pulled up, which doesn't.
So because this clock is keep pulling these 2 points to ground all the time.
Yeah.
Makes sense?
Yeah.
Okay. So whenever, if at some moment, if this one is higher than this one, which means this PMOS is opened up more, right? You got a bigger opening, and it's going to transfer the voltage here more efficiently. So we got more voltage here and more voltage here. Yeah, and it's pulling this down to ground even more. And this voltage becomes smaller. And this is bigger, this is smaller, just keep going like that, right? So eventually, if VNP is larger than VNN, what's going to happen for this voltage? VNP is larger than VNN, which means this is opened up more, right? So the voltage here will be put up to here more, okay? Which means the voltage here will be higher. And this is opened up more, wider. And this one will be put down to ground. So this will be 0, right? So this will be high. And this will be 0. So whenever you see whenever the sine wave is going up, the reference voltage is so the VNP is always larger than VN for a certain amount of time. Okay, so it's always larger. Then when this clock is faster than the sine wave. Just keep resetting these two pins, right? So what about this pin? What is this pin doing? If VNP is always larger than VN, it's the upper half of the sine wave. Remember, when VNP is larger than VN, what's the voltage here? Which is 0. Okay. If the clock is on, yeah, it's not changing anything. So you're getting a stable logic high here. Okay. Whenever the clock is running, it's not affecting anything here. But what about this one? That one is high, right? That one is high. And this one should be low, but whenever the clock arrives, it turns it on, pulls it to the ground, and this becomes 0, and this becomes high. But whenever clock is 0, what's going to happen? Whenever clock is 0, it makes this point to be a floating point, right? Then what? Then the comparator works, and it's going to pull this up to VDD again, because this is opened up more, right? It's going to pull this up. So what's happening if this clock, when the clock is working here, what's happening to this node? It's charging and discharging. From where? VDD, from this path. Okay, open it up, discharge it. However, it is able to source current from VDD from this path. It's going to charge it up whenever clock is low. Cut the path to the ground whenever, to make this point floating, and is able to will be able to charge it up from VDD from this path. So it's going to oscillate, right? That's why if we run a simulation, so when VNP is higher than the reference voltage, this one is large, or this one is logic high, right? But the other one is oscillating. So when VNP is larger than VN, that's a node I probed. It's one of these two. And so the inverter, you can see why they want to use the inverter here, because it has one more pass from VDD to source more current, and also a ground to discharge it. So it's buffering these two nodes to make it more clean. It's performing like a buffer. It is able to drive. I didn't connect any caps here, but it will boost the driving capability for the output. So here's a question, okay? So we expect either 1 or 0 for the output of the comparator. Remember the SAR logic? We need either 1 or 0. And if you look at the, this is one of the references I posted online, you can find it. This is one master thesis from a UAE graduate student. Anyway, it's good. You can see that there are a couple of different versions of the comparators being used, and this is one of the schematic of the SAR ADC that uses the one we just simulated. Okay, so what is this? That's a CDAC, DAC, but using capacitors. We are going to run the simulation for this one later. Okay, instead of using a what's that called, the R2R ladder, it uses a CDAC. That's a DAC as a SAR logic. As a control logic here is a bit different, but the ones we used works, so we don't have to use this structure. Just 8, how many bits? I guess 8. It didn't draw all the intermediate ones, but there are 8 D flip-flops or 9 D flip-flops, and that's a TI D flip-flop you guys drew there, right? We can use the ones we, the simplified version, right? The other one we analyzed. Some control logic. That's a comparator's input. Oh, that's interesting. See, CMP, input getting to the mux. And let's see, that's what I'm thinking actually. CMP, right? CMP is directly being fed into the SAR D flip-flop. You can see the two outputs, you just need to use one of them. So you got 2 outputs, right? You don't have to use both of them. So only one is being used. So you are expecting either this one or this one. But for the DC voltage here, it's easy to use, just the logic 1. But for the oscillating one, we actually want to use the 0 here, but it's oscillating. How do we accurately, latch that 0 to the D flip-flop? Yeah. But the clock can be different. I mean, I don't know yet. I don't have the answer for you guys yet. But I'm also reading this thesis. Hopefully I can find out how do we modify it. Because there will be delays, so maybe that'll be fine if you use a clock, the same clock. The best case is if you are able to sample that comparator's output, So here's a comparator's output, right? It's oscillating. It has a 1, right? So this is easy. It's a 1 everywhere. But for this part, we just need these values, right? The ideal case is you got a clock rising edge right in the middle. It's just always sampling that, which is perfect. Is that possible? So the clock, if you use the same clock, I don't know, but there will be time delays. You know what I mean? Even though you couldn't see it here, could you see it here? If I zoom in, if you use the same clock, okay, you may have to reverse it or immerse it. Sorry. For example, we are sampling VLP. Okay, I use a clock. No time delay, but I think the simulator probably is not that accurate for the real world circuit. There will be more delay, but there are so many other ways to divide the clock. If you have a clock here and you divide it into 2, or no, actually you multiply it by 2.
There's only one gate between clock and VLP, isn't there?
One gate?
Yes, the time delay shouldn't be that big.
Oh yeah, exactly. It's just 1 animals. Yeah. It happens immediately, pretty much. So if the clock is high, it's pulling that to ground. And the inverter. So it's actually the inverter and the capacitors of the animals as the time delay. If you make this inverter huge, a huge inverter, let's see. Very good at that. Want to do VLP, right? Let's make this huge. It's already huge. Let's change this one to micro. No. 100A. Wait, is that going to make it? Yes. No, it's more cap. Should be larger. You'll learn digital models later. It will be larger time delay. It's more caps. It's bigger caps. So the gate has a oxide, right? Yeah. Let's see. I don't know. I think that's what we did in the lab, right? One of the labs used a huge inverter and you see a significant delay. You remember that one? Let's take a look. I don't know yet. Hopefully it still works, you know? Still works. Cool.
A little bit.
Yeah. Oh, it's later. Later is good, right? Because we need 0. Yeah, we need to sample 0. But this is probably not a good way to do it. I'm just saying you can change, modify the clock. So for example, you shift the clock 180 degrees, right? Or 90 degrees. Yeah. So you'll be able to sample in the middle. There are a lot of ways to do it. But is this how he did it? I don't know actually. If you see that this part, the comparator's output being fed into the mugs, and so you can choose either, what is the output for this one? Yeah, another question is, I don't know what is this one doing here. That's another type of flip-flop. We didn't use it and still worked. Okay, it's a different strategy of forming that timing logic. We use the counter to form the timing, and they must use something different here, like a mux and a different type of flip-flop. Yeah, need some time to explore it. So this is the first schematic, and there are a couple of other ones. There are all the timing logic. Yeah, that's it.
PhD on something?
No, masters. It's not PhD, masters.
So did they just like sit there and sit in electric or whatever and just lay this all out for hours and then run it and it didn't work and they just laid it out again?
Why did it? Oh yeah, you mean just doing circuit design?
Yeah.
You can even get a PhD out of it. For circuit design, so the research, the purpose of research is to read all the literatures, right? All the other papers people published, and then convert it into the ones like works for you, and simulate it and demonstrate that this is my design and works for this specific type of application. Right? And then you just do some investigation into it, do the comparisons, to the plotting, power consumption, you know, all these bandwidths, then get a paper, then graduate. Okay, so let's get back to the circuit. So there's one, it's not a wide swing circuit, which means if this input, there are only PMOSes receiving the analog input, okay? So which means you can imagine that if the voltage input here is very high, this is not working anymore. It's not a wide swing version of it. So how do we verify it? So the way I did it is I make these both side voltage to be like 0.99. Okay, see if it still be able to detect that change. You know what I mean? Where's the sound wave? Where's the sound wave? Oh, I have to change the sound wave as well, right? So I'm gonna move everything. I'm gonna change this one to, can we do it 500 maybe? Yes. Okay. Yeah, so you can see that stops working whenever the voltage here is very close to the voltage from the other side, and they are both very high. It's not working anymore, okay?
Wait, he's saying that P is greater than all times?
Yeah, so only this part is V in P is larger than V in N, right? So it's supposed to oscillate. But you can see it's not actually us. How do you sample at 0 here? You couldn't. It stopped working. Okay, and that only has 2 99s after the decimal point. If you have like 0.99 or something, it's going to be even worse. But can you imagine these are the units here are voltages, but usually the voltage here are like millivolts, 100 millivolts. So it won't work for the small voltage and also small voltage swing, but DC output is very high. It's not working anymore. And there's another version, which is Y swing. It's called real to real. So it has another counterpart here, which is the NMOS version of it. You can see the two PMOSs here are receiving the analog voltage, but also the two voltages are being fed into the two NMOSs here. So whenever the voltage are very high, it's going to nicely turning these two NMOSs on, so they're still able to swing in the channels. So see here, I use 0.99. It's even worse. And we'll see if this will be able to detect that. Yeah, because I see the parameters I set up. It's making this more difficult. What is happening here? Okay. This is 0.99, but still giving you really nice. This is nice because the clock frequency is very high. That's why. If you want to see if they are, but you can see that it's down to 0, right? You got somewhere to sample. But if I slow down the clock, it's gonna work. The reason I have to increase the frequency is because this is super narrow, but they are still getting oscillations. So what if I use 99 to make it better, and it can compare with the other one?
Oh my God, like you just gotta photosynthesize. Okay. That's all right.
It's a lot better than the last one. At least we can tell, right? It's good. Okay. So higher won't be that bad. I don't think you guys are laying it out for the course project. It won't be that bad. Yeah, it's a lot of fun laying out circuits. Mm-hmm. That's a very typical symptom of graduating from my class, digital class. Always thinking about stick diagrams, getting addicted to it. Okay.
No, green. No, boring. It's really boring. It's got no profile. It's just pretty sure. It's not black tea, it's green.
Mm-hmm. Are we going to work on that for the analog?
He approved it.
Okay, so this, then the discussion here will be helpful. All right, let's see. Let's review it first, okay? So clock not. Okay, clock not. So the signal here, the clock not here, at the same phase as this one, okay? So whenever this is high, if this is high, this is high, right? What's happening? What's happening? If this is high, this is high, what's happening? This is almost, right? If this is high, this is ground. It's going to transfer ground to here, and it's going to ground the almost, so it's not sampling. And then it's resetting this VG here as well. So it's holding. Yeah, V high is always on. Yeah. It's buffering, it's protecting this almost here. Adding one more channel resistance to protect it, because it's, this voltage can be pretty high, can be like 2 VDD. Remember we boosted. If it's 2 VDD, you just turn it on and off. It's probably will make the lifespan of the drain here shorter, I guess. That's what I read from the paper. So it's just adding one more layer, protect this one. Okay, so this is always on. And if this is high, what's happening? Again, holding. Yeah. So if this is high, shorts to ground, the ground will be sent to here, will be sent to here. So VG becomes ground. And you can see voltage ins here, the sampling, right? And this guy is sampling, okay? If VG is 0, this is not going through, which means it's holding. The cap is holding that charge, the previous charge. So whenever this is high, this will be shorted to ground. This pin, it will be shorted to ground. Okay. And it's pulling a VDD from here to charge this up. Because whenever this becomes ground, whenever this is high, it turns this on, and it's going to start pulling this point to the ground. Whenever you pull charges from one side of the cap, it's going to pull charges from the other side as well. It's AC. It's not a DC voltage. If you pull it, it's called instantaneous activity or something. It just happens like a spike, right? You pull it, so the AC signal is going to pass the cap. It's going to pull this point to ground as well. But won't directly go to ground because you have a VDD connect to it. So this one will continuously source as a source for this plate of the cap. It's going to charge out the cap on the other side. So current dumping into the bucket. I know it's not intuitive, right? I couldn't see that happen, but it happens. If you do the simulation, it's going to charge out the cap. So if you pull this point, you pull it, it's going to charge out the cap from the top because this is on. Why is this on? Because it passes what to here? VDD. Yeah. Why is passing VDD? Because you got a higher gate voltage compared to VDD, so you almost can pass the entire VDD. Why you are getting a higher voltage than VDD? Because of the charge pump. why the charge pump works? See here again. If I pull this one to ground, if I pull it to ground, pull it down, what's going to happen? It's going to source current from the voltage from the top rail, the power supply, and passes NMOS. Again, this is NMOS. Okay, passes NMOS to here. So it's going to pass. It's going to pass VDD. Not exactly VDD, but very close. It's going to VDD minus VTHN, right? To here, if you pull it. And then, because the inverter is a clock, the other cycle is going to push it up. So that charge is going to be stored here, because whenever you push this up, this one is pull it down. Okay, if you pull it down, you got a VDD here. Wait. So it previously stored a VDD, and then you push it up, you're getting a 2 VDD minus VTHN. Why is that? So this pin swings between VDD and 2 VDD, no, VDD minus VTHN to 2 VDD minus VTHN for this point. It's like open it up, sourcing a VDD here, and then, so it's the same as this one, right? It's oscillating. So you can do it on the paper.
It makes a lot more sense.
5% more of the chance of understanding it.
Yeah, I have to start at it for a while. like what I did. That's why analog is more difficult than digital, because it's just changing all the time.
Okay, after years.
I think that's a requirement.
Okay. Let's just look at this one instead of other ones, then we'll call it today. Okay, 4 more minutes. Let's see if we can do it. Okay, VDD, VDD, VDD. NMOS, they're all NMOSes. They're all NMOSes. So clock, shorter here is the same clock. Right? If, for example, at some point, this one got a falling edge. This one will be rising edge, right? So falling edge is going to do what? And I see rising, let's do rising edge first. Okay, rising edge is going to do what? It's going to charge this up to VDD, right? We'll turn this on. So you got a falling edge here, because this is on, it's going to source current and charge it up. You got a VDD here as well. And then the next cycle, what's going to happen? Next cycle goes up, and this goes down, right? If this goes up, should we look at this one first? Wait, they both store VDD for now. Actually, VDD minus VTHN, right? It has some loss in. Oh yeah, this one is VDD, yes, and this one VDD. But let's ignore that minus VTHN for now. It's minor, okay? Minor. Yeah. Then what? This one goes up. What's happening for this node right now? This one pull it down, right? At that moment. So if this one pulls it down, it's gonna pull This is still on, right?
Yeah, so if that's still on,
It's still on, it's gonna keep pulling that, but this is not changing. I don't think this is changing.
so it's just stuck.
It's stuck there. Yeah, stuck. But this one, because this one is pushing, right? It's pushing, it's charging this up. So what's happening is it's gonna boost this one to VDD1 plus VDD. It's pumping another VDD to it.
Okay.
It works the same as, did you learn that voltage doubler in analog? Have you learned that yet? Voltage multiplier, voltage doubler.
Oh, where you superimpose like a sine wave on a DC?
All the dials, string of dials. You haven't learned it anyway. So the one I built in the summer with company, it's a voltage doubler, voltage multiplier to amplify the DC voltage from 500 to 3000. So it's able to pump it up. So you couldn't see why it happens, but if you pump charges on one side, it's not losing any voltage, so it's gonna charge it up to 2 VDD.
Are we gonna pop a capacitor somewhere? Yeah.
Because it's not passing to here. Why?
Yeah, it's still open because the other side was weak. So it's still passing.
But is it passing 2 VDD to here? Because you got a higher potential here and lower potential here, is that able to pass it? No, why? Because it only has VDD here for the gate. If you treat this one as a source, even though it's 1 VDD, so it's gonna stuck, right? It's not able to pass and because this is a very strong voltage. It's a voltage power supply. If you can short to it, it's gonna pass. It's gonna short everything here to here. It's gonna make it VDD here. But actually, it's not, because you are not opening it up that much. It's only VDD here. You know what I mean?
I'm so glad there's not like 20 people in this class.
So 2 VDD. If you have you got a 2 VDD. Can you pass 2 VDD to here? No. NMOS is not good at passing that. And you should open this up to 2 VDD plus VTHN in order to pass the whole 2 VDD to here, right? But now you only have a VDD here. That's why this one will stuck. I got a VDD here as well, because it's right there, it's a power supply. It's gonna stuck. It's gonna charge it up to 2 VDD. And this is shorter to here. And we'll open this up more and pass the whole VDD here, because I got a 2 VDD for the gate.
So when that gate turn on?
This is on, yeah, this is on. So VDD is passing to here. This one? Yeah, you got a 2 VDD here to open it up. That's why it's not losing anything anymore, because you got the whole capacity to pass it. Yeah. Now this NMOS is good at passing VDD, because you got a 2 VDD for the gate voltage. We talked about that last time, right?
Yeah.
And why was that? Oh, it's a VDD is not zero. You couldn't turn a PMOS on. Then you need a zero, but how do you make it more zero, lower than zero? You couldn't do it. Like negative voltage.
But why do we need it lower than zero?
Oh yeah. How do we get a zero here? Just keep grounding it? Yeah, anyway. Yeah, but I just
gotta keep it only like 3 people every semester.
I make it 3 people plus. I change the material. If I got 30 people in there, I won't do this kind of discussion session.
Yeah, so I mean, especially after